We are going back to the moon. This program is real. It's exciting. Built hardware. We've launched rockets. We're getting ready to send humans around the moon for the first time in 50 years. They're going to go farther from this planet than any other human being has been.
Hey, Karl, how's it going?
Good. How about you, Erum? What's going on? We had a week off and you did some travel.
Yes, yeah. I went to Nova Scotia up in the Maritime Islands of Canada, and it was amazing. I think a lot of people go to Acadia in Maine, which is beautiful, but it's so packed. There's so many people there. I think it's also because it's a small island. But in Nova Scotia, there's Cape Breton Island, and there's no one there. But
Yeah.
it's so beautiful. It's so dense and lush. They have streams going into lakes, going into ocean. And there was one point where I was standing near all of them. With one site, you could see all of them. It was at a beach, and there was a river going through the beach into the ocean. And then there's a lake right behind the beach. And I was like, this is so crazy. And it was nice and relaxing, and being in nature and appreciating Earth was a wonderful time to spend the vacation. Actually, you were really busy the past week with your sons and traveling.
Yeah. So for those of you listening for the first time, this is the Grow Everything podcast, where we talk about the impact of biology as technology in all industries. And yes, I did have a crazy couple of weeks. I traveled from Brooklyn to Richmond to drop off my youngest son, Felix, at the University of Richmond. And then I traveled back up to the Adirondacks, which is always a huge reminder, just like with you, being around nature. And the impact of climate on the forest is something I'm very interested in. And then came back here. And then I just went and saw Aliens. Have you paid attention to it, or what's your take on the Aliens franchise?
Oh, I only watched one of them. And so long ago, I don't remember like different scenes, but I need to get into the franchise. I know that the new one came out. How was it? Did you like it?
So it's worth saying that at a certain point, the franchise does become about genetic engineering, because it turns out, and spoiler alert, the aliens were engineered. So this particular episode, the seventh installment in the series, Aliens Romulus, is called an interquel. So it's both a sequel and a prequel. It's supposed to take place between the first and the second Alien movies, the ones with Sigourney Weaver, which, it is worth saying, were very radical in their time. I ended up listening to a series of podcasts in French, of all things, about Alien and aliens and their impact on filmmaking. And it was the first time, when the movie was introduced back in the 70s, 1979, it was the first time that there was a female protagonist. Another thing that's super interesting about the Aliens franchise is that those early movies also had very diverse casts. So you had different genders, different races, much more reminiscent of Star Trek. Star Trek was also known for having aliens, and all the people who were on the original Enterprise were all different races, all different species. So that made it interesting. It's a romp. You know what you're going to get, but it's interesting to think about what happened between Alien and Aliens. And there's some special effects, not the monster special effects, but the special effects of the space station. Again, this is a big spoiler alert. The space station starting to crash into one of the rings of the planet that they're on were just amazing, because these rings, like the rings of Saturn, are just ice and rock. And so as a spaceship gets into them, it's going to disintegrate because the spaceship can't handle all those rocks. So that was very cool. But it does involve genetic engineering. There are genetic engineering labs on the space station. So very cool. You know what you're going to get, mostly.
Cool. Is it more of an adventure, or is it more horror or scary?
It's definitely more of a horror movie.
Is it? Oh,
Yeah.
I don't like scary stuff. So I'm interested in the genetic engineering part of it. But
let's just say it's more of a bloody thriller. And you're just waiting for the aliens to show up, and you're always anticipating where they're going to appear and how they appear. But there's face huggers. I bet face huggers will be a big theme for Halloween this year.
I don't even know what those are. What's face hugger? And a tree hugger.
Yeah. Space huggers kind of look like crabs that jump on your face and then insert themselves through your mouth into your body.
Wow.
And yeah, it's pretty hardcore.
Yeah, that's really hardcore. There has to be aliens on other planets.
Yeah, I mean, we have aliens on this planet.
Like?
Well, I mean, let's think about it. I mean, there's animal species that lived in the time of the dinosaurs that still exist. I mean, we know plants, for example, ferns are some of the oldest plants in the forest. And didn't you mention something about organisms that live in the deep sea that maybe weren't impacted by the big comet hit?
Yeah, yeah. But they're all still stem from the origin of life. They still are part of Earth species. I'm talking about life originating on other planets. And perhaps they traveled on an asteroid and came on to Earth, and they're somewhere in the deep sea or somewhere on our planet. But I definitely think that this is part of the excitement of space exploration, which is a big topic of our interview today, which we'll get into. I'm really excited about it. Where would life be on the other planets in our solar system? Let's just focus on our solar system, not the billions of other solar systems that are out there. But where would it be?
So there's basically three places, apparently, though there could be more. It all has to do with water. It's the theory that life needs water to survive. But I think that's only if we're looking at water that is based on carbon-based organisms. So the places that life would exist on, potentially exist in our solar system besides Earth, of course, Enceladus on Saturn's moon, and Europa, and then even potentially Mars. Those are the places that supposedly have water.
Oh, yeah. Yeah. Europa has subsurface oceans. Life on Earth started in oceans. We were talking about really, really old creatures living in the deep sea, the same species continuing. They could be in the subsurface oceans of Europa, just swimming around, building things. Maybe there's a whole city there. I think this is a great start of a script for a movie. Aliens, it's the sequel. Maybe it'll happen in Europa. Did they go to Europa at all?
No, so Europa was also the topic of a movie where there's a spaceship that goes there and they're there to explore life. I'm not going to spoil it, but it does seem like they find something, which is very interesting. But that is an ice-covered planet.
Yeah, I mean, there's also thermal vents, even on Earth, to studying the coldest parts of Earth and the hottest parts where there's all sorts of extremophiles and they are thriving. Io is another moon of Jupiter.
The fourth largest moon in the solar system.
Yeah, yes. So, and it has a lot of volcanic activity that the face of Io changes so much because there's so much volcanic activity happening. And then there's also a moon that's cold, but has thermal vents. The temperatures has the range. Something has to be going on, even if it's at the micro level. And it's so interesting because it makes me think about scale. We see ourselves in a scale of humans being from little kids that are like 2 feet to, I would say, there's people that are 7 feet tall. So some basketball players, I guess. But that's the scale which humans and animals are. But we have the micro scale. And like, could there be very intelligent micro scale beings that are making cities and doing things and have their own society, but they're just in the micro scale? It's possible, right?
We don't know. This is the subject of science fiction.
Yeah, science fiction until it becomes science fact. You need to have hypotheses. Everything's science fiction until you do an experiment.
Yeah. So I think that's a perfect segue. We've been talking a lot about space. And today our guest, who we're really happy to have, is actually an astronaut, Dr. Kate Rubins. You met Kate Rubins before I did. When did you meet Dr. Rubins?
I met her at Synbio Beta last year and then met her again at the recent one. And wow, I was blown away. I mean, I'm definitely a fangirl. I guess you can say that. She's amazing. She's the one who really got me excited about space and biology. And there was a lot of topics that she discussed and a lot of colleagues and other people in the space industry, I guess you can say, that talk about space biomanufacturing and biology being the key technology to have when you're going into space, when we're talking about long space missions. Did you just meet Kate this past year?
So you had mentioned Kate after meeting her last year. We tried to get her on the podcast, and then I ran into her at this year's Ferment conference in Boston, had a long conversation with her, sat behind her, and then learned that she was the first person to actually do PCR in space. And she has been in space for something like 300 days. So she's the fourth most days in space by a US astronaut, and she's performed 4 spacewalks. So she's fascinating. And I think we should just let her take it away, and then we'll reflect on what she said. Dr. Kate Rubins, we are so pleased to have you on the Grow Everything podcast. We know you've been extremely busy. The first two times we talked to you, you were busy testing spacesuits. Hopefully it's okay that we can say that on this podcast. But we're so happy to have you here today. When are you going back to space?
Oh, that's a big, important question. You should ask my boss about that one. I don't know. But I'm super thrilled to be here today. Really excited to do this podcast with you guys.
And I think the way that we understand it is that you're on the Artemis mission. So does that actually mean you're going to the moon, or is it you're on the list of potential moon astronauts?
Yeah, so we have a list of people who are working as Artemis team members. And what that really means actually is that we're helping out with the development of the Artemis hardware, testing the hardware, working with our NASA programs that are designing all of this. So pretty much anybody is a potential candidate. Anybody in the astronaut office is a potential candidate for these first Artemis missions. We've just named the Artemis 2 crew so far, and that's the crew that's going to go around the moon in an Apollo 8 style mission. So super excited to get that crew named. It includes some of my really good friends and a colleague of mine that I flew in space with on my last mission.
Wow, that's amazing. That's amazing. Kate, I'm so excited to talk to you. I have seen you speak at SynBioBeta last year and this past year. It's always mind-blowing. It gets me very excited about space and the work that you're doing specifically around biology. For our audience, we talk about space a lot, and I think a lot of that stems from my super interest in it. I always bring it up as it's like, okay, so you're making mushrooms. How about making mushrooms in space? But for us, we would help our audience understand, how do the unique conditions of space affect biological processes, whether it's low Earth orbit, whether it's the vacuum, whether it's the moon. I mean, give us a little bit of flavor of what's going on in space.
Yeah, space it's a really interesting environment because it's got all these things going on, like microgravity and radiation, distance from Earth. And so this ends up affecting every living system. So it can influence the way that plants grow in space. It influences how bacteria replicate and what gene expression signals they give off. It influences animal behavior. So for example, spiders. We sent spiders to space and they get really confused when they first get there, and they actually can't really build their webs very well. The webs look all messed up for the first few days. But like any living organism, they adapt and they figure out how to do this in microgravity. And so really some of the most pronounced changes we see are in human beings. This is one of the most studied animals in space. And we see things where space and microgravity affect everything from the immune system. We see some immune system degradation to bone loss and muscle loss. We get cardiovascular changes. So our blood flow in our jugular vein actually can stay stagnant or even reverse in space. We don't have that same kind of pulling down of all the fluid to the legs. And so we can see all kinds of medical problems because of that. We're starting to learn about some of these more. But really the amazing story about humans is we've got some problems in space, but we've never evolved to be in a space environment. And given all of that, we can still send people to space and their eyeballs don't explode and their human bodily functions tend to work. So there's a lot about the adaptability of living systems that we're learning in space. And that helps us understand a lot more fundamental questions about these systems when we can put them in this environment and then watch them change due to microgravity or radiation.
Well, one of the things that I always picture is astronauts doing a lot of exercise on a bike or on a treadmill. And you say that your blood flow in your jugular reverses. How does that exercise impact that?
Yeah, so exercise is one of the really important things for us. It's actually health promoting behavior. When we exercise, we do it 2.5 hours a day, and we have resistance that we can work against. So it's like going to the gym and going to squat rack and putting a whole bunch of plates on a squat rack. We can work against resistance. And so this is one of our countermeasures that actually helps stimulate bone growth. So when we go into space, we have a breakdown of the bone, a really massive breakdown of the bone. It's this use it or lose it philosophy. Same thing with the muscles. If you're just floating there, you don't actually really need your bones and muscles very much. So exercise sends the signal to your body. This is still important. You better go ahead and build some of that bone back up that you've just broken down. So that's important for stimulating our physiological processes. Down the road, we might use something like lower body negative pressure to help draw some of that blood down into the lower body to help this issue that we're seeing with the blood flow.
That's incredible. So you are a molecular biologist by training and education and experience. We would like to know when you're in space or in the International Space Station or even your colleagues, what biotech tools are being developed to study and mediate any health effects or create new biological processes. What does biology look like at the International Space Station?
Yeah, that's a great question. It's something that I've been working on at NASA for the last 15 years. When I first got here, we had the space station. It's like we built the lab and we had the lab benches and we had some equipment. But our equipment tended to be these really large pieces of equipment like a combustion furnace or a glove box. We didn't have a lot of the molecular biology tools in space that we want to use for these experiments. We've started doing things like building up the ability to do PCR in space. The ability to pipette in space was something that I worked really hard on when I first got here. The ability to have a rodent colony so that we could do animal studies. Plant facilities have existed for a long time, but we've been really upgrading those. And then we're looking at additionally, how are we going to be able to do these molecular biology experiments? So it's not like an Earth lab bench where you just put things on your bench and you pipette. Everything floats. Fluids behave completely differently. So in addition to the equipment, we've had to develop the processes to do these experiments in space. After building that basic lab, we're now pushing it further. In 2016, we did the first DNA sequencing in space and followed that by RNA sequencing. We demonstrated CRISPR. We demonstrated that we could barcode and multiplex in the sequencing and that we could actually sequence directly from a bacterial environmental sample. And so we've pushed all of these newer techniques and the ability to do that in situ, point of care, like right there in station. Where we're going in the future are things that are modular. We still don't have a lot of space inside the space station, and we don't have a lot of power. We generate all of our power on solar arrays. So we can't really think of our lab equipment like something that you would have at a major university lab or a hospital. We've got unlimited bench space, all the power in the world, and high-speed internet connectivity. Those are all resources, and we're competing against all the other things on the space station that need those. And so the kind of things that work in space are also biotech tools that would work more in a remote environment. Let's say you're doing field work in the Atacama Desert or something in Chile. Those kinds of things where it's small, it's portable, it's ruggedizable, maybe it doesn't have a huge power draw, it doesn't require constant internet connection. You can save the data and packetize it and send it home. That's where we're going. I'm really excited because the whole field's moving in that direction as well. We want more point of care devices. And those are the kinds of things that are good for space. In addition, as we develop these things for space, there are things that I've seen in my missions that I think, gosh, this would be an incredible piece of equipment. I used to have a lab in Congo, in Central Democratic Republic of Congo. The stuff that you develop for space would work really well in these remote settings. So there's a really interesting synergy there.
And just so our listeners know, Kate, you were the first person to ever do PCR in space. What was that like?
Yeah, we did. So we did PCR and then we did DNA sequencing in space. That was really cool. It was definitely an experiment. We sent the hardware up to try to see if it would even work. So we didn't know if DNA sequencing was going to work. Fluids behave differently. When bubbles get into your fluid in space, they don't go anywhere. There's no buoyancy-driven convection. So the bubbles don't just automatically rise to the top and the fluid goes down to the bottom. The bubbles just sit there and they stay there. And if you shake them, sometimes they make themselves a whole bunch of smaller bubbles and they're just persistent. There's a lot of things that are pretty different when you take a standard piece of lab equipment up to space. So we said, we're just going to bring it up there and we're going to try it. And we assumed things would go terribly wrong and it would be an interesting way of finding out what we needed to work on because, of course, things were going to go wrong. I'm really happy to say that this was probably the first time in my life that an experiment worked the first time I did it. I mean, this is not how it goes normally on the lab bench, right? So if you're going to have it work in space. So it actually worked really well. We were using a device that had microfluidics. It didn't have a huge amount of complicated lasers to align. So we were already using a ruggedized small footprint device. And that worked really well. So then we were able to expand to a bunch of different kinds of sequencing, different use cases. We worked a lot on the sample prep, how we're going to do sample inputs. This really rough environmental sample, we have to split open the bacteria and it's all gooky and you've got to clean it up. That was important that we demonstrated that it's not just these beautiful, pristine, pre-prepared libraries, that we could go all the way from our environmental sample through sequencing, and then even have onboard data analysis. So we had a miniaturized supercomputer up there that we could use to do some computing for the database matching and then have a data package. And that all happened in space.
Wow.
Could you give us a hint as to how biotech advances in space maybe can contribute to what we know about humans here on Earth?
Yeah, I think we're learning a lot about what happens to the human body when humans are in these interesting, stressful environments. And they're not environments that we can put people in on Earth. For example, the low dose radiation that we're experiencing is not profound enough to make huge genomic changes. But as we start sending people to the moon and to Mars, we're going to get a lot higher doses of radiation. And so we obviously want to protect our astronauts, but there's going to be some risk exposure. And so we can study that scientifically and try to understand more what are the mutations that are happening at the genomic level? How could we do cancer prevention with some of this data? We're learning a lot of things about bone loss and muscle loss. We have that in astronauts. And so what you lose in space in 1 month as like a healthy 40-year-old is the same as an 80-year-old osteoporotic woman would lose in a year. So we have these healthy subjects. The astronauts are always the test subjects as well. And we put them in this environment where they got sudden onset osteoporosis. And then we bring them back to Earth and we help them recover from that. And what we found when we did that was if you lose bone in space, you can recover it when you're back on Earth. But when you recover, if you think of your bone as like a PVC pipe, that the cortex of the bone is a PVC pipe, and then there's like a tensile web in the middle of the PVC pipe. If you lose bone and you start to lose that web of connections, they're not going to grow back. What you'll grow back is bone. You'll make your PVC pipe bigger. You'll grow bone around your cortex.
Hi, a quick shout out to our sponsor, Messaging Lab, the force multiplier for biotech. Your biotech company is making the world a better place. You know that, we know that. But does the world? There's a big reason why some biotech companies attract investors, sign up customers, and get attention. That reason is strategic communications. At Messaging Lab, we translate complex science and economics into compelling narratives. And we have done that for the most successful biotech companies across healthcare, agriculture, personal care and beauty, materials, and the list goes on. We're here to make sure your ideas not only get heard, but resonate with your audience. So if it's time to amplify your company's voice, visit messaginglab.com to explore how we can elevate your story and grow your business.
One of the results of that study was how important it is to not lose bone in the first place and how much this resistive exercise that we are doing can actually prevent that bone loss. So you name the human system, there are things that we're learning about it. And where biotech comes in is the ability to make those measurements in real time in space. So things where we can look at an analyte in the blood is very important. We're interested in using the capability of doing sequencing to look at human gene expression in space. Maybe we want to see what happens to the microbiome as you're in this closed loop environment where water is recycled. We're on a very limited diet. The food's affected by radiation. I think it's really in the ability to analyze all of these strange things that are going on in the human system.
Oh, yeah, that's incredible. I mean, something that we've been talking about a lot is the microbiome, whether it's human or environmental, and how that plays a key role here on Earth, but obviously too on the International Space Station. I know you mentioned it a bit when you spoke at SynBio Beta, but can you tell us a little bit more about how you see the role of synthetic biology supporting different systems for space travel? So you mentioned waste recycling, food production. What are you excited about when it comes to SynBio and space?
The whole entire topic.
Yeah. Okay, sorry. That was such a big question. Everything.
So we're actually working on a roadmap for SynBio work with NASA right now, and that's going through some final reviews. And I think we're going to have that out hopefully early next year. We've broken that down into a few different segments. We're looking at things like plants and nutrient production, waste recycling, SynBio for human health and disease, and spacecraft monitoring and environmental aspects of SynBio. And so you can imagine that you could have a whole lot of different SynBio applications for this trip to Mars. And so what we're really thinking is we're going to maybe do the test bed demonstrations on ISS before it sunsets in 2030. But the application is really maybe for a long duration lunar colony or for a Mars voyage. It's going to take 2.5 years to the red planet. So we know that we're going to have limited cargo. And basically what you launch with from Earth is probably all the molecules that you're going to have. You may have supply depots along the way. So that changes our perspective on waste and our recycling and this closed loop aspect. We have a lot of closed loop systems on ISS. Our water is 98% closed loop at this point. But we're pretty wasteful with things like our carbon molecules and our hydrogen molecules. So we capture CO2 from the atmosphere, and then we turn around and we dump that overboard into the vacuum. So when we're talking about going to Mars, I always say that every molecule counts. It's all important. And we need to think of a job and a recycling path for every single molecule. So carbon capture becomes incredibly important. And what can we use that carbon for? We want to be able to, for example, capture the nitrogen out of urine, make some kind of fertilizer, and then use that to grow our plants. We could use things like solid waste and disinfect that and use the cellulose in that as a substrate for some 3D printing or additive manufacturing. So a lot of these are like, I say this, it's just so easy, right? We're talking 10, 15-year technologies, but that lines up well with our timeline for Mars. So we're really interested in what the research is that's going on right now out in the community, because people are working on all of these problems on Earth as well. Carbon capture, bionutrient production, environmental sensing, waste recycling and repurpose. All of those are really heavy hitter Earth problems. And so there's a lot of people in the community working on that. Our job is to take those things and figure out how do we make that small enough? How do we get it down into a single site in a spacecraft? How do we make the power and the mass and the volume really low? But it's an extreme edge case. So I like it in that it pushes the engineering forward. If you have this problem where the only carbon you have is the carbon you launched with, unless we happen to find a whole bunch of it on Mars, then you really have to think very, very carefully about the waste chain. So on the ISS right now, we have cargo vehicles come up. We put a whole bunch of trash in them, and then we send them to burn up in Earth's atmosphere, and that's 7,000 pounds of cargo every 3 months. We're not going to have that on the way to Mars. We're not going to get resupply like that, and we are certainly not throwing stuff away. And so eventually the goal is going to be everything in the spacecraft gets reused. And so it's built for this purpose with that in mind. So maybe our food packaging is something that we can then break down and use that material in additive manufacturing. We've got to think about what our waste chain is doing and how that's producing a useful product for us end to end.
I could see that also being really useful for the circularization of the economy in general. And that is something that we've talked about a bunch on the podcast. So you mentioned Mars, which is looming large post getting up to the moon after Artemis. As the Mars rover is cruising around the planet, it's always questions about, is there any life there? Is there any water? What do you think the likelihood of us finding anything that is alive either on Mars or any of the other celestial bodies in our solar system?
We think that the conditions were there. So there is the possibility of having life on Mars. I think it's a really important question to answer. Was life on Mars something that helped seeded life on Earth? Did we all get seeded from the same thing? Is this something that arose naturally in the abiotic conditions in our early solar system? I think we need to go look. I'm just going to be completely uncommitted in my answer about whether or not I think we're going to find it, because I think it's too hard right now. We don't have enough information. So there's some tantalizing conditions. We need water, and we definitely have evidence of that. I think overall, in terms of finding life in the universe, it's either going to be really common and not too hard to find, or it's going to be incredibly uncommon. I think even if it is common, we get a little anthrocentric in thinking that from our little small corner of the galaxy, not even a blink in the history of the universe that we're going to run into that life. Obviously, the universe is vast. What I think people sometimes get lost on is the time scale. So what's the likelihood that life develops? It's going to have to be real common for it to have developed in our few 100,000 years of existing on this planet out of 14 billion years. These are deep philosophical questions that you want to talk about after work with a cold beverage. I won't stake a claim in any of these. I just think it's super interesting. I'm glad we're going. I think it's really important to do these kinds of experiments and exploration. And it's just awesome to think about that we might be able to answer some of those in my lifetime.
Yeah. I'm reading your friend's book, Chris Mason's book, The Next 500 Years, Engineering Life to Reach New Worlds. And it's been incredible. Yeah, he talked about, for example, forward contamination. If the rover had any microbes on it and it's on Mars and it finds microbial life, is it Martian life or was it from Earth? It's a whole debate, especially when it comes to extremophiles. But the book I thought was super interesting when it talks about engineering humans for going into outer space. So my question for you is, would you get engineered if it's safe and effective? And what would you like to be engineered for?
Oh, well, I think that safe and effective bar is going to take so long that I'm not really worried about this overlapping with my career field at NASA. I think it's maybe our kids or grandkids that would be engineered. And of course, there's a lot of ethical questions that come up surrounding that. So I think the first question is, are we going to be able to do safe and effective human engineering? And when would we be able to do that? If you think about, do you have a requirement for humans to be engineered to be able to do the job of astronaut? That starts making me morally go, ooh, I like the idea of space exploration and that it's done in a democratic way and it's open to people to do. So I think I would have a hard time with saying, hey, we were going to require our astronauts to be engineered to resist radiation or this or that. But I think that's some very high level decision making that would come from our policymakers. If it was voluntary and it was safe and I decided to become engineered, I would definitely pick radiation resistance.
Yeah, I think I would too. So looking ahead, how do you see the integration between space research and biotech shaping industries here on Earth? Are there any exciting developments that you're anticipating?
Yeah, I think number one, I'd really like space research and biotech to be more integrated. I try to go give talks at conferences, but oftentimes the biotech sector or the academic molecular biologists don't think about space. This is not something that's at the top of their mind, but it should be, because when you're talking about closed loop cycles, small point of care devices, low power, things that would be useful in really rural, remote locations, there is a bit of synergy there for space. And I would like to see those two communities become more entwined. And so maybe we need to have a conference about this for remote researchers or people that are looking at working in developing countries and space researchers and people that are interested in this closed loop recycling, and bring all those folks together. But I do think the things that I'm really excited about are systems where it can do a lot of the analysis. Like, you give it a sample and you get the data out of the back end. If you're going to do sequencing, you swab the sample and you've got to extract it. Then you've got to prep the library. Then you've got to put it into the sequencer. So these are very manual steps and they're done separately. There's these great robots that are giant that can do this for the big pharma and biotech companies. But in terms of having small point of care devices that go swab all the way to sequence, we don't have a lot of that. So I'm interested in synergies there. And I think that's one of these things that if we build it, we're going to find amazing use cases for it. So people may not be thinking that there's a big market for it right now, but things like the nanopore sequencer, right? Once you have a sequencer that you can put in your pocket and has low mass requirements and doesn't have to have a lot of this fancy recalibration, people are using sequencing in places that you would not expect. So I think if we extend that to the sample processing as well, number one, this makes this a lot easier where you don't have to have a technician or a specialist. So you could go into rural area in the remote corner of the world and you can train local folks on how to collect samples and run the sequencer. And you don't need to worry about having a technician from this company fly in to fix it. So I think that really this modularization and this idea that nothing is wasted, and we need to really think a lot more about all the consumables. If you're doing an experiment in a molecular biology lab, look at your trash can by the end of the day. Look at all the stuff that we throw away. So how can we make these experiments not only end to end, but less wasteful, or have their output be a designated input for something else? I think there's a lot of great work that the space community is really motivated to figure this out for a Mars mission. And I think our community on Earth, both from a sustainability perspective, but also from novel materials. And if you're forced to recycle all your molecules, you think about different and creative ways of doing something. So I think it's a forcing function for innovation as well in our biotech community on Earth.
That's incredible. Okay, we have one more minute. I'm going to ask you one more question. So besides Earth, what's your favorite celestial body and why?
Ooh.
And that's a hard one.
Well, I'm drinking the NASA Kool-Aid right now, and I've really got to say the moon. We are going back to the moon. This program is real. It's exciting. Built hardware, we've launched rockets. We're getting ready to send humans around the moon for the first time in 50 years. They're going to go farther from this planet than any other human being has been. So just the fact that we're alive and that we're going to witness a moon landing in our lifetime. And this is a different kind of moon landing. So Apollo went to a lot of these equatorial regions where it was lit the whole time and facing Earth for calm reasons, and it's a little easier to land there. We're going to go to the pole. We're going to go to the south pole of the moon because that's where we found water ice. And so this was actually only a recent discovery in the early 2000s. We used to think the moon was bone dry. And then we sent a couple of satellites in there and we crashed one satellite in the moon and we flew the other satellite through the plume and we were able to discover the signature of water. So the big question is, how's that water distributed? Is it molecular water and like it's just tiny little molecules and a whole bunch of regolith and moon dirt? Or is it big chunks of ice? Because that makes a big difference. How easy is it to collect that water? And once we have that water, we may not have a lot of it. So again, these things like closed recycling are going to be really important. But once you have water, you can do all kinds of things. Number one, you can keep humans alive. We're really hard to keep alive. You need water to do that. Yeah. Number two, you can split the water and make oxygen. You can split the water and you can make rocket fuel. A lot of rocket fuel is just hydrogen and oxygen. The discovery of water allows us to think about having a permanent base on the moon. The reason that we want to go to the South Pole, in addition to water, is the geology. So there's craters on the moon that have never seen a beam of sunlight because they're so deep. They've been excavated and the shadow is too deep. The sunlight can't penetrate it. And so these are some of the coldest places that we have access to. Some of these get down to 40 Kelvin. We've not sent humans to 40 Kelvin before. So it's a great engineering challenge. But what we can find, because these never see sunlight, is that volatiles are condensed in there and they're not evaporating. What this gives you, if you think about the moon, it's like a collection depot. It's like the Rosetta Stone for the solar system. So moon and Earth existed 4+ billion years. But the Earth has vegetation and life and continents that keep moving around and tectonic plates, and we subsume a lot of the really interesting geology. So these rocks aren't available to us anymore in this really old time scale. The moon doesn't have this air and it doesn't have plates moving around. So things are frozen there in a way that you can actually look at a geologic and a molecular level and see what happened in our solar system from 4 billion years ago to 1 billion years ago. So we get things like solar wind depositing particles in there. We get little bits of asteroids that go there. We've got a lot of questions about how our solar system formed. And the ability to answer those is found in the geologic processes of the moon. And so this is where I take my departure from becoming a hardcore molecular biologist to being such a geologic fan. But I think it's really interesting in terms of thinking about what we're going to do there and how biology is going to help us. It's going to help us a lot, I think, with the ability to live on the moon, to go study this geology. And my favorite experiment that's not funded by NASA or in any official plan there is I want to go to the moon and do a negative control. I want to do a map of all the biology that we bring with us. So this is in an answer to your earlier question about what Chris was talking about in his book. We're going to bring life with us. We need to be very careful on Mars. We're going to have to sample life with completely sterile rovers and probably nowhere near the humans. But what if, as we went out on these spacewalks and left the lunar lander, took samples and started to sequence the samples and look for, probably organisms aren't going to be alive for very long, but we can look for their molecular signatures, their RNA and their DNA. And we can see the persistence. So we're going to do like a spatial temporal map of the lunar surface as the humans are just out there walking around. And we build ourselves a signature of when dirty humans and their dirty equipment go to another planetary body. We know that there's no life on the moon. So everything we find, we know that we brought there. So yeah, definitely nothing that NASA's actually proved, but I'm going to keep talking about it and maybe somebody will think it's a really good idea someday.
Oh, that's so
Amazing.
Cool. We'll advocate for it too. Okay. So we'll sign the petition.
All right. Well, this has been amazing. Kate, thank you so much for taking the time to speak with us today. We hope we can get you on again to have a longer conversation, but we really appreciate that you were able to come on. Thank you so much.
Yeah, absolutely. It's been so great to talk to you both.
Erum, what did you think of that episode with Kate Rubins? You have been a huge fan of hers.
It was too short. I don't know if anyone noticed, but I was very nervous because I'm such a big fan of hers. But any minute with Kate is amazing, illuminating, just so inspiring. So that's what I took away from the episode. But definitely could talk to her for another like 3 days straight, probably longer than that. If she had a class of some sort, I would sign up for it. But there's so much to think about. I mean, there's the near term of what's happening at NASA, where she works. So the Artemis mission, going to the moon and going back there and perhaps setting up a moon base. That's really exciting. But there's other missions that are scheduled or being planned, and towards what end. I would love to learn more about the resources NASA has, their collaborations with other countries and then other private organizations. But regardless, Kate, I just am so blown away by her experiences and her thinking about space exploration. What about you? What were your takeaways?
I mean, I think to me, the big thing to take away, and I got this a lot from the episode with Elizabeth Reynolds as well, is that all this technology that is being developed for space has huge applications here on Earth, and there is a huge opportunity for developing more space tech. There are trillions of dollars of value to be created, and we've only just begun. So Kate mentioned a couple of opportunities that they're looking for when it comes to miniaturization, and that's just barely scratching the surface of all the things that we need to do. I mean, if you watch any space movie, space opera, I think of The Expanse in particular, you just see the amount of technology that needs to be developed. You're a huge fan of For All Mankind. I've not watched it, but I would imagine that they show the development of technology. And again, there's so much technology to be developed for space, and the impact will not only be on space, but also here on the planet. So I think we need a lot of this.
Yeah, towards the end of our interview, Kate also had that call to action, like develop for space. It's going to be helpful for Earth as well. And using space as a way to have parameters. A lot of technology that we have today, of course, was made because of space exploration. They were made for space, but okay, well, there's applications here on Earth. And across so many different fields, not just electronics, and you said miniaturization, but of course, biology. And there's a lot. I think one exciting thing that we didn't really dig into too much because we didn't have much time was pharmaceuticals. How do you manufacture personalized pharmaceuticals quickly and just enough for the person that needs it, so that you can have some raw materials, you can say what kind of disease you have, and then it generates the molecule for you specifically. That would obviously have huge implications for Earth, but to be able just to focus on saying, hey, look, we need something for space, because there was a whole topic about this at SynBioBeta, where pharmaceutical drugs that they bring on a space mission or to the ISS, they have a half-life. So if they're not used, they're just waste. And then that's like a waste of weight to bring up there. And I think being able to materialize pharmaceutical drugs is huge.
And you mentioned waste, and Kate also mentioned it. And I know I've said it on the podcast before, but waste on Earth is a multi-trillion-dollar industry that we're just seeing the beginning of. We're seeing a lot of companies look at waste streams as potential resources. And in space, it's even more critical to be looking at waste as a resource, because I think Kate mentioned that today's coffee was yesterday's urine. Or something like that.
Today's coffee was yesterday's coffee was yesterday's coffee was yesterday's coffee.
Yeah. But like you say, it's expensive to take things into space. You want to keep things light, and anything that we can start to manufacture up there is going to make a huge difference. I'm just really looking forward to, especially after coming out of Aliens, and wondering when we start building ships in space as opposed to building them here and shooting them up there. I have a feeling we'll see that during our lifetimes. I just don't know if it's going to be in the 2030s, 2040s, 2050s. At some point, that's going to be a thing. But I think waste is something I'm always happy to talk about because I think it's so fascinating. And space is something that we need to get more people to come on to talk about because it impacts the life sciences in a big way.
Yeah. Waste is huge. I want to quote Nicole Richards of Alonia. She says, waste is a failure of imagination. And waste is like a man-made concept. There is no waste in nature. Everything is used. So I think also if we take the principles of Earth's dynamic and how Earth functions and how ecosystems function and apply it to spaceships and going out into space. And one of the things Chris Mason talks about is generation ships, because going to some of these celestial bodies will take thousands of years. Even with the most advanced technology that we have, they calculated if there was fusion technology or antimatter technology, it still takes thousands of years to get to some places. They didn't mention things about wormholes yet, so that could help speed things up. But besides that, though, you're going to need to be in space for a long period of time. So how can you create pretty much a satellite of Earth? And I'm going to quote our friend Evan Bayer. We played his episode in the last episode. He calls Earth spaceship Earth, but I'm like, why don't we make a spaceship from Earth? That's something that I've been thinking about a lot. Rather than using metals, Earth isn't made of metals, it's made of soil. But anyway, I am digressing, but I think it's a deep thought, just thinking about how do we mimic Earth as a spaceship?
Yeah, I mean, Evan was quoting the famed architect, futurist Buckminster Fuller, who had written a book, I think in the 1960s, called Operating Manual for Planet Earth. And I think the moment we start considering Earth as a spaceship is a moment where our consciousness shifts and we start to take everything that we do on this planet a lot more seriously. I think, as you say, wasted failure of the imagination. Nature surrounds us. It makes life possible. And the moment we start to look at our planet as a spaceship is, I think, the moment we all start to respect it in a much different, more profound way. And I think with that, we should end the pod.
Yeah, absolutely. Stay tuned for our next episode, which is going to be an exciting conversation with Vega Shah of NVIDIA. So it'll be a great, great conversation. If you have any questions, have any recommendations for guests, want to leave a comment, please reach out to us. We have multiple ways of connecting. You'll see that in our show notes. Also, we have an amazing community that we're building through our Patreon page. So we would just love for you guys to be a part of our closest community, especially as we bring on more and more guests. So we look forward to hearing from you, and thanks so much. We'll talk to you soon.
See you later.